change gears here a little bit, and I'm going to go through a bunch of different types of things. Most of this stuff I don't expect you to know. I am just kind of, it's interesting and you should know about it. So this is what we call an electrode. So this is a glass electrode. Now there's all types of different electrodes. There are pH electrodes, of course, which basically measure the hydrogen ion concentration. There are silver electrodes that measure the silver ion concentration. There's chloride electrodes. So there's a bunch of different types of electrodes out there that measure different types of ions in solution. So the basic design, so let's talk about just a pH electrode. Okay, so this is a pH electrode. Again, basically it is a closed glass vessel. And inside this vessel, we have a silver wire, and it's coated in silver chloride. Okay, so it's a silver wire coated in silver chloride. And then it's in a solution, a dilute solution of hydrochloric acid. Then there's a very thin glass membrane. This membrane is actually thinner than a human hair. That's why if you've used them in labs, you'll notice that there's usually a plastic crown around the base of this thing, and it's to protect this glass here. A fairly large, or not a fairly small stir bar will exert enough force to crack this thing. And these things are $800 each. Okay, they are not cheap. Okay, and basically what it is again, it's the hydrogen ion in solution. Okay, so, and the thing is enclosed, so it has some hydrogen gas being produced. So basically it is this and then some reference electrode. Now the reference electrode in our case is at silver. Okay, so we have our hydrogen. Again, this is the way it's going to look. It's going to be the hydrogen gas in equilibrium with the hydrogen ion, the acidic proton, and 2 electrons. Okay, so we could write the half reaction. So this would be for the whole, but we could actually write the half reaction, right? So there would be the standard cell potential for that half reaction. There's 2 electrons being transferred, so N is equal to 2. And then this is going to be the concentration of our products raised to the coefficient divided by the concentration of our hydrogen gas. Now, I know this is weird, right? We now have mixed. We have a molar concentration, and then we have the partial pressure in atmospheres. Now, the reason we can get away with this is because this remains constant. This just remains constant. And again, we assume it's 1 atmosphere. So this just remains constant at a value that we arbitrarily say is 1. Okay. So again, this is just the standard H2 going to H+, which of course is 0, right? We base everything off of this reaction. So that's just basically 0. Again, we assume that this is constant at 1 atmosphere, so it just becomes part of the equation itself. So now we're down to this, okay? Now, property of logs allows me to take this value and bring it out and multiply it. So it's actually 2 times the log of the hydrogen ion concentration. That's just the property of logs. If I have a log of something raised to a power, I can simply take that power, multiply it by the log itself, and now all of a sudden it's just the concentration of that particular species. So I can bring that 2 out, okay? Now I can cancel out the 2's. Now I have the negative log of the hydrogen ion concentration. Well, we've seen that before, right? The negative log of the hydrogen ion concentration is just the pH. So I could replace the log in the negative log of H+ with pH. So I can now say 0.0592 volts times the pH. Okay, so then the cell potential then must look like this, right? The cell potential is going to be our half reaction, right? Which is, we just determined was this, plus whatever reference electrode that we use. Again, in the case of the pH electrode, it is often the silver chloride. Okay, so that then looks like this. The pH of the solution is just equal to the cell potential that's measured, okay, minus the reference electrode, divided by 0.0592 volts, okay. So, and like I said, this reference cell is normally silver chloride for pH electrodes. Those of you who have Chem 113 here at Altoona, you're going to do an experiment that actually kind of deals with all of this here, except that you'll be measuring the concentration of silver. So it's going to be slightly different, but again, it's this whole same idea that you're going to be using in that lab. Okay, I just want to go through a bunch of different battery types. Again, I do not expect you to memorize any of this stuff. This is just for your information if you ever wondered how some of these things worked. Okay, so this is what's called a normal Le Chatelier dry cell. So this is your, your AA, AAA, your C, D batteries. So this is just a normal battery, and it looks like this. Basically, it is composed of, we have a positive and a negative terminal. The positive terminal is in contact with a graphite rod, which acts as our cathode. Okay, it actually does not partake in the chemistry. It is just a conduit for the electrons, okay? The actual reaction is right in here. This is the magnesium 4 oxide, the zinc 2 chloride. It has some ammonium chloride in it, and then the carbon represents the graphite rod that's going on here. So that is basically our cathode. The anode is simply a tin shell that it sits in, and then usually there's some metal jacket around it, okay? So basically what occurs at the anode, okay, the zinc, the can that's actually holding all this together, is acting as our anode. So we can see that the zinc's going to zinc 2+. So the can that the battery is actually stored in is slowly being eaten away. Then again, within this paste, what's happening is the ammonium ion is reacting with the manganese 4. Okay, the zinc chloride is simply there. Remember, we need the anode to be in contact with its ions. So that's why the zinc 2 chloride's within the paste. But the ammonium ion reacts with the magnesium 4 to form magnesium 3, manganese 3 oxide. Okay, and again, it also produces ammonia, which is very corrosive. So if you ever wondered why, if the battery sat long enough, it started to leak. In other words, it formed some kind of crustiness all over it, usually ruins the inside of electronics. I don't know if you've ever seen that, but the reason for that is that the ammonia, first off, the can is being eaten away. What's holding everything together is being eaten away. Then this ammonia, which is very corrosive to metals, further eats away at the jacket itself, usually right where it connects. Okay, so this tends to be the weakest part. Then all of a sudden, this paste that contains all this corrosive ammonia leaks out and basically ruins everything in that battery case of that device. So this is just what we call a normal Le Chatelier dry cell. Now, this is the same thing is true for like watch batteries. So the Le Chatelier dry cell is also just an alkaline dry cell. You'll notice that it looks basically the same. The components are the same. This time we have zinc powder instead of the zinc metal itself, but the paste still contains the solid magnesium 4 oxide and still acts as the cathode. And so really you have exactly a very similar reaction. Instead of ammonia, the ammonium chloride, now they're using potassium hydroxide, okay, but it's acting as the same way. And now it's forming the zinc 2 hydroxide, releasing 2 electrons. And then again at the cathode, the manganese 4 oxide is being converted this time to this weird manganese 3 oxide hydroxide, and releasing 2 hydroxides in the process. So very similar chemistry to the Le Chatelier dry cell, and then this is just an alkaline dry cell. So the two are very similar, and when you buy batteries, you probably don't even know which one you're getting. It depends on what brand you actually buy. Then we have your car battery. Your car battery is actually a rechargeable battery. So these batteries that I've talked about, the alkaline dry cell and the Chatelier dry cell, they are non-rechargeable batteries. Once this chemistry occurs, it's non-reversible. But we can have rechargeable batteries. So again, this would be your car battery. And basically inside there, you have your anode, which is lead. Okay, it's pure lead. And then the cathode is just lead-4 oxide. And the whole thing sits in an aqueous solution of sulfuric acid. Okay, this is actually the #1 produced chemical in the world because there's so many of these lead acid batteries. Okay, the chemistry that occurs, the lead reacts with the acid, specifically the hydrogen sulfate, to produce lead-2 sulfate and releases more acidic protons and gives up 2 electrons, which again, of course, come out of the negative terminal. You use it to drive whatever you need in your car, and then goes back to the positive, the cathode, right? And there, that's hooked up to the lead-4 oxide terminals. Okay, so that's these middle guys here. They react with the acid in solution to reproduce the hydrogen sulfate that was consumed. Okay, uses those 2 electrons and then converts it back to lead-2 sulfate. So this is why you can recharge these types of batteries. Okay, notice that the chemistry is very similar in the anode and cathode of what's being produced. So this is kind of a requirement for rechargeable batteries. Okay. An early type of rechargeable batteries, I don't think you can even buy these anymore. You may have heard of them though. They were called NiCad batteries. Basically, they were nickel cadmium cell batteries. They were slightly complicated. Basically, they were just a big roll, okay? And the roll consisted of 4 layers. There was just 2 separators, which is just basically very thin pieces of cardboard or paper. Then you had your negative electrode, right? You had your anode, okay? And in the anode, you basically had cadmium. So in this sheet, it was kind of they call it like a jelly layer. So it's kind of gelatinous, okay? That's why it's held together by these pieces of paper. In that sheet was solid cadmium. Now, the problem is cadmium is highly, highly poisonous, okay? I'll come back to that. But so the cadmium then reacts with the hydroxide to produce cadmium-2 hydroxide, releasing 2 electrons, okay? The electrons then would pass out. There's little tiny connectors here for the positive and negative. This picture is only showing the negative, but there's another one for the positive. And basically they are connected to the bottom and the top layer, okay? And then we had our other one. So this is this positive electrode. They say it's a centered positive electrode. And it is just this weird nickel oxide hydroxide compound that when it picks up electrons is converted to nickel-2 hydroxide, okay? Again, releasing hydroxide. Okay, so we have this common component again between the oxidation and reduction reaction. Again, why this thing is chargeable. Now, I'll also note that nickel compounds tend to be highly poisonous. The cadmium is really, really, really poisonous. So the problem with these, there's several problems. One, there wasn't a lot of recycling going on at this time, and these things were just being thrown in landfills by the tons, which would poison most of the local groundwater. Again, why we have regulations basically are there to protect us. So they basically, these also had another problem too. They had what we call memory. Now that was a big problem with early rechargeable batteries. What that meant is that if you only used the battery to half its voltage and then recharged it, it would remember that. So it would only work for half the time. Okay, so every time you would do that, you kept losing a little bit of the life of the battery until finally the battery just, you couldn't use it. You'd recharge it, it'd work for literally a few seconds and die again. So that was a huge issue with early rechargeable batteries, was this thing called memory. So you were constantly going through these rechargeable batteries, because if you didn't charge them properly every single time, and even if you did, they still slowly died over time. They wouldn't hold their charge anymore. They then moved to a much safer, still not really safe because it used nickel, but this was a nickel metal hydride battery. Okay, so they were called nickel metal hydride batteries, and basically, again, there was this complicated layer, just like the nickel cadmium, where it was basically the 4 sheets, the 2 separator sheets, and then we have the positive and the negative layers. Okay, the negative layer, of course, was the anode, and it was just a metal, depended on a lot of things, but different metals were used. And if it's a metal hydride, that means that the hydrogen ion now is negative, right? So this is our negative. And so this was positive. So it's going from positive to 0. So that, of course, was reduced. And then basically just formed water. So that was at the anode. And then at the cathode, they again used this same nickel oxide hydroxide component. And again, we can see the similarities in chemicals between the oxidation and reduction half reaction. Again, one of the reasons why these types of batteries are rechargeable is because of similarity in the chemistry. So again, this got rid of the cadmium, which had, again, very toxic, very poisonous, and it was expensive for the same reason, because of its high toxicity. So it greatly reduced the cost of these rechargeable batteries. But even these NiCad batteries had issues with memory. Again, they would lose the amount of charge they could hold over time. And if you didn't recharge them properly, they lost that very quickly. Okay, nowadays we have solid state lithium iodide batteries. I'm not going to get into the chemistry of these. Because it's relatively complicated. I'm trying to make an image that'll make that easier to understand, but basically you're going from lithium metal to a lithium iodide crystal, okay, and back and forth. And again, it's not like the chemistry that we normally see for our regular batteries at this point in time. Again, much more complicated process, but basically it is metal lithium going to lithium ions, okay? So that's why they call it the lithium ion battery or lithium iodide battery. Now, nowadays, they don't use iodide so much, okay? They've moved to even more complicated salts than just lithium iodide, but the original ones simply went from lithium to lithium iodide. And it is a complex. It's not just iodide. It is a very complex material. Then we have what's called fuel cells. Now, there's all kinds of different types of fuel cells. The most common fuel cell is a hydrogen-oxygen fuel cell. This type of fuel cell is used a lot, particularly for if you're going to be an astronaut. They constantly use hydrogen-oxygen fuel cells. But even today, we use hydrogen-oxygen fuel cells in a lot of different applications, particularly for generation of electricity in remote areas or as backups. And it basically looks like this. We have a tank of hydrogen and a tank of oxygen. The hydrogen reacts with a catalyst, which is just basically platinum. It separates the hydrogen atoms, and then the electrons are stripped away. The hydrogen ion passes through what we call a polymer exchange membrane. It just basically allows the hydrogen ions to skip along SO3 minus entities. So it just skips along until it gets to the cathode, which again is just platinum. Okay, the oxygen comes in, then the hydrogen combines with the electrons coming back and oxygen to form water. So what's really nice about this type of combustion, okay, is that it does not produce carbon dioxide. So hydrogen fuel cells were hoped to be the fuel of the future, except that there's a lot of issues with hydrogen. Hydrogen is an extraordinarily dangerous, extraordinarily explosive gas. So you generally would have to generate, instead of having a tank of hydrogen, you would have to generate the hydrogen. Or they tried for a long time to store the hydrogen in metal hydrides because that's a much safer way. You can hit a metal hydride with a hammer and it's not going to explode. But even a small spark will set off a tank of hydrogen and take out an entire neighborhood. So you wouldn't want to drive around with a tank of hydrogen strapped to the bottom of your car. A small fender bender would literally wipe out thousands of people. So probably not a good idea to do that. But this is how it works. So the hydrogen simply came in to the platinum where it was separated into the hydrogen ion. Okay, so we see the hydrogen ion. Then the electrons, we use them, comes back to the other platinum catalyst where it combines with oxygen coming in from the atmosphere, just from the air. And again, the only exhaust is water. So basically, at the anode, we have H2 going to water, releasing 4 electrons. Okay, and then at the cathode, we have the oxygen recombining with the 4 electrons in the hydrogen ions to form our hydroxide. Okay, and so when you add these 2 half reactions together, you'll notice that the hydroxide cancel, 2 of the waters cancel, so that leaves 2 waters over here, the 2 hydrogen reacting with the oxygen to form the 2 water. So you can see the overall reaction looks like that. Okay. Okay.